Good morning, everybody. How are we going? Before we kick off today, I have one thing to say, which I did send out an email notice, so most people should have it in their inboxes already. But if you don't, or you haven't read your email, or actually, if you didn't receive it, there's a problem, which means that your UNSW email address isn't working in some way or another, because usually anything that I send out as a course notice goes to everyone. But we've just moved a couple of due dates. Basically, we've moved everything out of week 6. So there was a lab that was potentially due on the Monday of week 6. So for the lab purposes, we're just treating week 6 like it doesn't exist. So the week 5 lab, which is your current lab, some of you will already have it. Some of you will be having it over the next couple of days. That one will be due on the Monday of week 7. So if you want to, you could potentially not do any of that work in week 6. I mean, like, chances are the lab work you're going to finish in week 5 anyway. But the big one I think that changed was that the assignment got moved back. So originally we had it due on Friday of week 6, and this is just something because there was most of the time to do the assignment was actually before the end of week 5. So we just had it originally at the end of week 6, so it was like, okay, if you didn't finish it in time, you can still work on it when you've got some free time in flexibility week. I mean, people don't always have free time then, but you know. But it being flexibility week, the UNSW is doing some maintenance and things. So the CSE building is actually being turned off for for the Friday of week 6, and then it will be so that was actually going to be turned off during our due date. So we've moved our due date to the Monday instead, which means that basically everything from before flexibility week is going to be due on the Monday of week 7. The other thing I should mention is flexibility week next week is like an unofficial week, so there won't be any tutorials or labs running, but the lectures will still be running, but none of the lectures will have course content that hasn't been taught elsewhere. So what I'm planning is that one of the 2 lectures will be a revision lecture, which is just basically a Q&A. Like, we're not going to cover any specific content. We're going to allow people to just ask questions, and we'll answer whatever questions are there. And the other one's going to be a talk about professionalism that I have given several times before. So it's become a staple of this course, but it's not necessarily, I mean, it's not really about computer science, nor is it about programming. It's a wider kind of look at the things that you might want or need if you want to become a professional eventually. Yeah, so just checking. Matthew is asking if sharing of custom auto testers is allowed. I have to think a little bit about that and maybe have a look at it. But chances are it's okay, because it's just a way that, like, if it's just something that, like, puts input into a slide program, then it might be okay. But it also depends on, like, what else it might be doing. Let me hang on to that one and throw around some ideas, maybe with some of my tutors, to see whether this is actually, like, how this is going to affect other people doing their assignments before I give you a concrete answer on that. Vincent, you're asking about the extension portion of the exam. I assume that you're asking about the extension portion of the assignment rather than the exam. Yes, the extension portion is doable for students who are new to C programming, but it depends on how well the course is going for you so far and how much time you have to spend on it. So I think that anyone could do it with enough time. But whether that time is within the 3 weeks of the assignment or not is up to you to decide, because everyone's going to be a bit different. Okay, lots of questions about the assignment. I'm going to leave them for now because I don't think I'll be able to take that much time in the in this lecture to answer a whole lot of assignment questions. Joanna's there though, so you can ask questions and she will answer some of them, depending on, I mean, like, she's really there to answer questions that are, specific. Oh, well, not necessarily specific, but at least questions about what we're learning, not necessarily like picking at individual things about the assignment. But if you do have questions about the generic ideas in the assignment, oh, someone's come up to say hello. Then you can always ask the forums and stuff like that. Okay, let's roll into what we're talking about in the lecture. 1 second. You might want to see the lecturer in charge while I deliver their content. Okay, what did we learn last week? So we looked at functions, and we were extending functions last week to libraries. We also looked at arrays, but we were extending arrays into two-dimensional arrays. So this was us taking two subjects that we'd already introduced earlier and just expanding them a little bit further than they were before. And the other thing we looked at last week was quite a big topic that we're going to expand on as we go through, so don't worry if you don't fully understand it yet. But we're looking at pointers, pointers being variables that are specifically used to store memory addresses, and then thinking about the ideas of how we're going to use those memory addresses to look at other variables and things like that. And we looked at the idea that putting pointers into functions changed in a way what we could do with functions. So it's not necessarily having a function with multiple outputs, but it's a function that can affect multiple variables. And the other thing which I think may have, well, when we were first working with arrays, may have confused people, is the idea that arrays and pointers work in a very, very similar fashion. They're not exactly the same, but the name of the array, if you pass the name of an array into a function, it actually gives you access to the memory that's in the array. So there was a rule that I was saying that if you passed a variable into a function, the only thing that you would get is a copy of the value of the variable in the function, as opposed to if you gave an array to a function, you'd actually be able to change stuff in the array. And so there was a subtlety there that if you'd been experimenting with arrays before I told you about pointers would have seemed very confusing, because arrays seem to break that rule. But now that we know that the name of the array that gets passed into a function is actually the memory address, we know why. We can actually affect the elements of the array from inside a function. Okay, so let's have a look at what we're covering today. I'll just bring this back up to me. We're going to do a little recap on pointers, because pointers deserve a recap, and we're always going to need to, like, anytime we have the more complex parts of the course, I think it's important for us to go over them multiple times. But we're also going to look at debugging today. So we're, like, what I'm doing is, like, as we go through the course, we're not just looking at, like, how to build things in C. We're also always going to be looking at, like, what are the other things that programmers do? What are the other things that professional programmers have to do? And debugging is, like, one of the biggest things. You've actually been doing lots of debugging already, but instead of teaching it early when we only had a whole lot of very, very small programs to work with, like only our labs and things like that, I decided to wait until you have your assignment. And so now you have the capability and, well, the need to write a big chunk of code. So it depends, it depends how big your assignments are going to be. Some people's assignments are going to be, a couple of hundred lines or something like that. It's very easy to get lost in a couple of hundred lines. So I'm going to teach you about some of the processes that we might use to correct mistakes or correct errors in our code that we call bugs. And we're also going to introduce a new variable type today. We're not going to get too deep in this, because we'll go deep on Friday. This is another one of those things where I'm going to show you the topic and not really do any demos. on the day I show it to you, but on the Friday then I'll do a demo of that topic with some extra stuff. And those are characters. So we'll have a variable now that we can use for letters. So letters of the alphabet, but it's not only letters of the alphabet, it's other things as well, but we'll go into that more when we go deeper, when I start to talk about it in the slides and things like that. Okay, so quick recap on pointers and memory. So, the definition of a pointer again, in case people have missed it or just want some clarification. A pointer is a variable, like any other variable, so it's kind of a new variable type. But the interesting thing about it is it's kind of like a modification on the current types, and it's a modification on any type of variable where it says, I know that another variable is going to exist, so I know that there's going to be an int or a double or an array or anything, all of the other things that we know that are variables. And a pointer is a variable that says, I don't actually store the value of that variable or anything like that. Instead, the thing that gets stored in the pointer variable is the location of another variable. And locations in our computer we think of as memory addresses. So when we're looking at memory, we're thinking of memory as like one really big array of bytes, 8-bit chunks of memory, and the pointers have the capability of looking at each of those. So if I have an integer to a pointer to an integer, what it does, it says, okay, there's some memory location somewhere in my computer that I aim at, and I will see that and 32 bits of information just after that address, and I'll treat that chunk of memory as if it's an integer. So pointers are going to be able to do that. So them having a memory address in their storage, in a sense. So the pointers actually exist in memory as well. But they're going to hold a memory address that says, I'm aiming at another variable. And so we start to get to this idea that we don't often need the name of a variable itself to get access to it. If we know where it sits in memory, then we can use that memory address to get access to the variable. A lot of the nice things about this is some variables are hard to pass around on their own. When we get later in the course, we're going to start building up actually really, really big variables that are made up of multiple other variables. Arrays are actually already a good example of a really, really big variable that we may not necessarily want to be copying in and out of our functions all the time. So a pointer is nice, and this is why the array works like that in default. Excuse me. The array works like that in default in that if we give the name of the array to something, we actually give its memory address. So a lot of the time when we want to pass things to functions, we want to give access to something in a function, we can give a pointer to a variable rather than giving the variable itself. Because when we give the variable itself to a function, what we get is a copy of the value stored in the variable. But if we wanted the actual variable, then it's nice to have a pointer to be able to do that. So the analogy that I liked to use for the pointers is that they're like street addresses. So somewhere in our world, somewhere there's a piece of memory, and if I want to give you access to that piece of memory, all I need to do is tell you where it is. And so that's the street address example. If I gave you, what were we using? I picked a random number like 250 Anzac Parade or something like that. If I tell you something like 250 Anzac Parade, then you will be able to find it. And I can make multiple copies of this idea of 250 Anzac Parade and pass it to multiple people, and they will all still be able to find the same place. So you can do something like that. You can create multiple pointers to the same variable. In terms of like the raw C code of it, this asterisk symbol is the symbol of the pointer. So we're going to be using it both to create the pointer and to use the pointer when it's actually happening. So this here is a declaration of a pointer. Now I've declared a variable before that so that I had something to aim at. You can create pointers without having something to target, but it's easier if we initialize it to point to the address of a variable, and that's where the and comes in. We've actually seen the and before because we've been using it in scanf. If you look up the actual specification for scanf, it will show you that what it's actually looking for is a pointer rather than a variable. So if you actually looked it up, you'd be like, oh, okay, so we've been using this for ages, and this thing's been wanting pointers. So we've actually been using pointers the whole way through the course without necessarily knowing. Because in the same way that this is a kind of an integer value, it's not kind of, it is an integer value, which can be stored in an integer. This is a pointer value, so a memory address is a value that can be stored in a pointer, and this is a variable that stores that value. So these two things can kind of be used interchangeably when we're working with pointers. If we just want to give a memory address to something, we could just give the address of a variable, or we could give a pointer that we've created previously using the address of a variable. So that's our creation and our addresses. Then we need to think about, oops, put my face. Oh, I guess I wasn't covering up that much of the text there. Which way should I go? This way. When we want to use our pointers, like one of the most important things we're going to want to do with our pointers is to say, this pointer is aiming at this memory location. How do I actually go to that memory location and then read the information that's in that memory location? And that's where we use the star again. So the star is our way of actually what we call dereferencing the pointer. So we think of the pointer as a reference to a memory location. So if we're thinking of it as a reference to a memory location, then the star says, I'm going to remove that at reference and use it to actually nearly travel to the location. So sometimes when I'm using the star on a pointer that already exists, so this is a pointer because we've created it. So its name is IP. The name isn't actually star IP. The star is just the symbol here to remind us that this has been created as a pointer. If I use it again as a pointer, then I'm just saying, this is the memory location I'm looking at. If I use it again as a pointer, but I put the star back on it again, so this is like reusing it. This is actually really similar to the square brackets in the arrays. They're used in a certain way when you create them, and they're used in another way when you use it. So this is the other way. So after it's been created, if I put the star on it, what this is going to do is it's going to follow the pointer to wherever it's aimed at, and then read whatever is in the memory that the pointer is aimed at. So this pointer is an integer pointer, which means that if we follow this pointer to its memory location, it will read 32 bits worth of memory there, and it will treat those 32 bits of memory like an integer. So star IP here will find the integer I, because IP was pointed at the integer I, and it will read this 100. So if you run this code is in last week's demo code there. The first thing it will say, because if we look at the pointer raw on its own, it'll tell us the memory address, and that was that complicated hexadecimal number starting with 0x, which is the symbol for the hexadecimal numbers and a whole bunch of letters and numbers. And then the second value that gets shown there is us actually dereferencing, using the pointer, following it to its memory location, then reading the value out of it, which is 100. So a lot of this stuff is fiddly. It takes time to learn, so it's just a matter of practicing this until the and becomes second nature to you, the star becomes second nature to you, and you remember there's two things for the star. One is the creation of the pointer, so the star is necessary if you want to make a pointer, and the other one is the usage of a pointer. You can either use it as a memory address, or you can use it to find the value of the variable it's pointing at. So once you get a handle on all those different things that pointers can do, then you don't get tripped up as much on just the raw syntax of what pointers are doing, and you can start to delve into like what are the logical and theoretical possibilities of using them. So there's like heaps of the techniques I'm going to teach you have that same kind of thing, where it's like, what is the reason that this tool exists? So when I talk about while loops, you can kind of see the reason the tool exists. Like, what if we want to repeat the same code without writing it more than once? It's reasonably obvious. But then the nitty-gritty is like, how do you structure it? How do you make it run? How do you make it stop? You know, and so we need to like learn these two different things. One of them is just like the nuts and bolts of making it work, and the other one is the theoretical idea of like, if we think about programming not as programming languages or learning programming languages, but abstract problem solving, then what we're trying to get to is a point where you can solve any kind of technical problem in an abstract system, and then you get that kind of thinking, which is like your kind of important long-term programming thinking, and then your sort of important short-term programming thinking is, how do I immediately at this point translate that into a programming language that can run on my computer. So we kind of want both of those things. This slide is very, very much about like, what is the nitty-gritty, just like, how do I get this code to actually work? Pointers can be simple, but they can also be very confusing. So it's like anything that's like this that is has, like, when I say simple, I mean it has just things that are right or wrong, because its syntax is just either the correct syntax or the incorrect syntax. Syntax, I mean, what's a good explanation for syntax? Just it being typed in the right way for the C compilers to understand what you're trying to tell it. And stuff like syntax is just practice. This is like learning vocabulary when you're learning a language or something like that. Whereas the idea of how do we use this to solve problems is a bigger thing to think about. So when we're thinking about using pointers in functions, we can pass pointers into functions. So we can use pointers as our input parameters, as we would call them, of this function here. And so when this happens, it doesn't break the rules of functions. The rules of functions still stand. That whatever I pass into a function gets copied in as a value, and I do not have access to this pointer that existed somewhere else, say in my main function that was given here. I think swap_nums wasn't even used in the main. It was used in the shuffle function. So the shuffle function was using this num1 or num2 pointer variables. But whatever pointer variable was given to us, we don't actually use the original pointer variable. We make a copy of the pointer variable. We create a new pointer here called num1 and num2. But the trick with pointers is copies of memory addresses still get you to the same place. So if I write down 250 Anzac Parade and give it to one student, and I write down again 250 Anzac Parade and give it to another student, they'll both be able to find the same thing. So these copies of pointers that are elsewhere in the program will be able to find the same variables. So this is a really simple one, which is like, this is the most simple thing I could think of that would use pointers in functions, but do something that our normal functions up until that point were never capable of doing. So they were never capable of swapping what two numbers were. At best, you'd be able to say, tell me what the first number or the second number is as my input, and we'd only be able to give one of them back as an integer. Whereas here, two integer pointers gives us the capability to look at two locations where there are integers and then modify them. And so this thing was just like, use a temporary variable to store one of them while you copy one over the other, and then copy back the temporary variable somewhere else. Yeah, so when we want to think about like the easiest level of what we're doing with pointers is something like this. And so remember that when we were using the star, what this is doing is this is accessing the memory location that num1 was pointing at. And if we're accessing that memory location, we're treating it like an integer then. Because it was an integer pointer. So if we follow the integer pointer to an integer, we can then use it like an integer. So we're taking this dereferenced pointer and storing its value in a temporary integer here. So it's pretty cool. There's a lot that you can do with pointers. We're going to go very, very deep into a lot of the things you can do with pointers, but we won't be doing that until after the break. So we're going to hit flexibility week, give you a week off to just kind of I guess process the first half of the course, and then finish the first assignment, which is kind of wrapping up the first half of the course. And then weeks 7 through to 10, we're going to do the second half of the course, where we're going to get into all this kind of stuff. And it gets quite interesting, actually. We start to build these kind of logical structures using pointers that lead on to a lot of other problem solving stuff in computer science. I've said this several times already, but I've got a slide on it. The pointers and arrays are very similar. So arrays are chunks of memory that contain multiple variables, and memory itself could be thought of as a kind of an array. It's not exactly the same, but kind of. And the trick is that the variable of the array stores the address where the array starts. So the location of, like if we ask for the memory address of the first element of the array, it will be the same memory address as just using the array without any square brackets. So either arrays or pointers passed into a function are going to give you access to a memory location that may be created beforehand. Okay, on to sort of one of the main topics for today. Alex, yes, I am wearing a Star Wars t-shirt, and right now I am peak culture from a particular era, which you can tell what era I'm from because I'm wearing a Star Wars t-shirt and I have an Aliens quote in my lectures. I remember hearing a joke someone was saying it was like a survival guide for college students. I think must have been an American thing, where someone said that these are the quotes you're going to have to learn because you're like your lecturers are going to make references and jokes based on these movies that were brought out before you were born. Okay, so debugging is really interesting. So this is something that I think I've said before, but we get this ratio of the amount of time spent for a professional programmer. So the amount of time, like, this is only counting the time that you're actually sitting in front of your computer working with code, because sitting in front of your computer working with code is also not a massive percentage of your time, because if that's the only thing you're doing, then you're not actually thinking about what problems you need to solve. You're not theoretically working with, the solutions, or you're not even working with other people and making sure that these problems are the right ones. So the thing that happens when you're working on code is you're roughly, say, 15% of the time creating code that works, and 85% of the time you're trying to figure out why it didn't work, and you're trying to make it work. So debugging is this thing that we have to do. And so in order to understand what debugging is, we need to first think about what is a bug. So it's a really old term. It came out about, I don't think it was actually the 90s. I think it may have been earlier. Sorry, 90s. What am I going to say? It's like 80s, which was like the era of modern programming, like when languages like C first appeared. C actually appeared in the 70s, but I think it gained a lot of prevalence in the 80s. But I think this is actually a term that comes from before that. I think it's from the 50s and 60s, when programmers used to use punch cards, like pieces of cardboard with holes punched in them, and they would feed that into a machine that would detect where the holes were, and that would be its binary, like whether there's a hole or not in certain sections of the card. And I don't know if this is exactly how it happened, or it was just a metaphorical talking about it, where the idea was that if a bug got into the computer, like you squashed a bug between the cards by accident, then the bug would fill in the hole and then the program wouldn't work. And so it was this idea that like it was like a bug got into it, and that stopped your program from working. Nowadays, programs, they're entirely digital, so there's no such thing as a bug that can, well, I hope there isn't such thing as a bug that can get into your RAM and flip the bits in your RAM. That would be potentially disastrous. But we still use the same term for them, and this term says that a bug is something that's stopping our program from working exactly one way or another, and what we want to do is be able to find these bugs, figure out why our program's not working because of them, and then fix them. So I've talked a lot about problem solving already, which is like a sort of high level analysis of looking at these things and trying to find out why our program's not doing what we want it to do. Debugging you could consider to be the low level version of this, where we're going to go into nuts and bolts. So today, actually no, let me go further into the slides. We'll go one concept at a time. So first off, what is a software bug? So anything that maybe we have written or not written, or we've structured our code in such a way, anything that stops the program from doing what it was that we wanted it to do, is something that we would think of as a bug. So generally, most bugs in our code are self-inflicted. It's not usually someone else working on your code. I mean, like, well, once you work professionally, there always is. But then you'll just be helping each other out finding these bugs. Like, you've seen a bit of this in code review processes and stuff like that. Or if you're working with other people in your labs or anything like that to try to work together. Or even if you're watching the lecture and you see me type a bug in and then chat goes wild. It's always funny when that happens. Those things are bugs. But there's two different types of bugs that I want to think about today that are the most common. So one of them is syntax errors. So as I was saying before, I defined syntax. Syntax is whether we're typing in the right stuff so that our compiler, DCC, or any other compiler can genuinely understand it. So this is grammar. You know, this is just, are we typing the code in correctly to make it work? But it's not just grammar. There can be other things as well. I have some examples today. But then there's logical errors, which are quite funny. And I'm hoping that I've given you enough experience with code over the past 5 weeks of your tutorials and labs and things like that, that you understand what a logical error is. Because I don't know if anyone's done this at this point, but you have picked up a lab question, and then you've gone, all right, this is what they want us to do in the lab question. And then you go and code it, and you come back like half an hour, 45 minutes later after coding it, and you run it through the auto tests, and it just fails all of them. And then you just go, what's going on here? My code works, it does what I think it's supposed to, and things like that. And you look back at the question, and then you say, oh, I didn't answer the question. I just wrote code. It's very nice code. It's working and stuff, but it doesn't answer the question that was actually asked. And so that's the funny thing that can happen, is if you're answering the question that wasn't actually asked, what you have is what we call a logical error, which is a type of error where we've done something that we didn't actually need to do, or the code is not doing the thing that we'd intended it to do, but it's perfectly written code. You know, it compiles and it runs, but it can compile and run and still be entirely wrong. So this is like knowing the grammar, knowing the vocabulary, saying a sentence that's entirely structured correctly, but it's factually incorrect. So that's the kind of thing that we're going to do sometimes with logical errors, is we're going to write perfect code that doesn't solve the problem. And so these two are very, very different. Right, one of them is about the nuts and bolts, and one of them is about the thinking. And so that kind of separation, this has become a theme of the lecture today, the separation between the low level and the high level. You get different kind of errors in each one. So I think I do this a lot. I introduce a topic, and then I start talking about it, and I forget that I actually had slides for it. So C has its own grammar, and this is what I was talking about, syntax. The only thing that is important to remember about C syntax is that it is much, much more specific than human language. When you're talking to another human, like I'm talking to you now, I could use many, many different words in many, many different ways to get the same idea across to you. I can say things that are not grammatically correct. I can say things that are wildly incorrect in terms of English grammar. But you're still probably going to get it. You're still probably going to understand exactly what I'm saying. I mean, I think even a lot of what I say could be considered Australian cultural mannerisms and have connotations that mean a specific thing. And I don't even know. Like, I won't even remember why certain people don't understand what I'm saying when other people do, because I'm so entrenched in a particular culture that I just kind of communicate in that way. And a lot of that is actually grammatically incorrect. Whereas C is going to be really specific on this. It's going to say, no, if you break the rules of how things work, then I'm just not going to listen. I'm going to say I don't compile this. Or I'll throw a warning out saying, okay, this doesn't make any sense. So even the smallest mistakes can cause a syntax error. So people would have seen the easiest kind of simple mistakes of just like, you forget to put a semicolon or something. Or as you're typing, you're trying to go too fast and you don't type a variable name exactly the same when you're trying to use it, or use a capital when you should have used a lowercase letter or something like that, and then your program just flat out won't run. Whereas a human looking at it would be able to say, oh, you obviously mean that same thing, because there's nothing else in here that has that name, so you probably meant that, and we're okay with that, but computers aren't. So this is the thing we've got to remember. Syntax errors are going to come up a lot more because we as humans are kind of more used to speaking to humans, and so we're used to having our little minor mistakes just disappear as other people can interpret them. So the other thing I think that's going to come up is we're going to use our compilers most of the time to find syntax errors for us. So our compiler is going to be able to say, I did not understand this, and you're going to be able to say, okay, if you didn't understand that, maybe I'm not writing exactly perfect C. The thing to remember when you're looking for syntax errors is the error message itself may not be the error. And this is the difficulty, is the compiler is not, as I said, not a human, not able to interpret your intentions. It can only interpret the code itself. And so it will look at the code and it will say, this is where something doesn't work. And that might not be the error itself. That might not be the syntax error that you've created. It may be the result of it, the consequence of it that is happening far later in your code. So this is why debugging is difficult. It becomes this kind of backtracking through your code from where the error was to what caused it. Hopefully the demo that I have today will show you a little bit about what's going on there. Just move my head out of the way of the text. The other thing, as I said before, logical errors. We can write a program that compiles and runs that doesn't solve our problem correctly. So we can have a syntactically correct program. And this is why this actually kind of goes in order. Usually we'll fix our syntax bugs first, and then after having fixed the syntax bugs, we'll look at our program and say, okay, given that it is correct C, now is it correctly solving the problem? So this is very much a human error thing, although one would argue that syntax errors are also very human error based. But yeah, did we read the question correctly? Did we understand what we were supposed to do? Or did we get caught up in things and forget why we were making the program in the first place? This is such a common thing. And this is really a programmer thing. Like, people make jokes about us, about the stereotype of programmers where, if you don't keep checking what we're doing, so as a manager, checking up on programmers and saying, are we still working on this problem? And the programmer's like, oh no, what's that problem? I found this cool idea, this super cool idea, and I just started implementing it. And your manager's like, that's not, we need to release this. We're going to lose millions of dollars if we don't get this release out on time. And it's like, oh yeah, but I got this cool problem. And it comes from this theoretical mathematician. And then if you translate this into code, it does this. And it's like, and your manager's like, how did you get here? How did we get here? We're supposed to be making this thing, right? So it's very, very easy to get, they call it nerd sniping. And it's the funniest phrase, where you just tell someone an interesting concept and then they get caught up in it. And then they just go deep into it, and they don't sleep properly, and they don't pay attention to what they're supposed to be doing, because there's a scientific curiosity happening which just grabs your attention and then takes you off into like this amazing world. It's very intellectually stimulating, but not very useful to the people who are relying on you to do things. It's a programmer thing. We do it sometimes. It's good to be aware of it, though. It's good to be aware of it. It's good to make fun of yourself, because when you do it, you have to be like, okay, I know, I'm sorry. Let's go back and get the real thing done. So again, we do that, and sometimes we will solve the wrong problem. So sometimes we will get confused as to what it was we were trying to solve, and we do something different, and forgetting the context of the problem is usually the reason why logical errors happen. So now, down to how we are going to find these bugs. As I said a second ago, we're going to use the compiler a lot of the time for syntax errors. It's not the only way that syntax errors are going to come up, because there are some syntax errors your compiler's not going to find, and those tend to be structural errors. So did I build a loop correctly? Like, the biggest syntax error that your compiler's not going to find, and it's just going to throw you into, is something like forgetting the iterator in a while loop or something. So if I'm making a loop and I forget to increase I at the end of the loop, that's a syntax error. But your compiler's not actually going to catch it. But we're going to catch most syntax errors with our compilers. And this is the one that I think that people have already trained on. So in the last month of me just kind of throwing out these lab questions for you to work on, and you trying them in labs with other with your tutor and things like that, or working on them at home just to hand in, you would have been doing a lot of like, this doesn't compile, why doesn't it compile? Running your compilers over and over again, try to get something working. That is basically the process of catching syntax errors. There may be a bit more nuance in it than that, and I'll show you some of the things that we can do. But then there's also the logical bugs, and we're going to use occasionally code reviews and things for logical bugs, but you do need to be able to solve these logical bugs on your own. So I'm going to talk about testing. Now, up until this point in the course, pretty much everything that we've done for you has had testing. We've done your testing for you. So the auto test is us writing your tests. Auto tests are all written manually by one of us. Some of them are really old. Some of the questions in the course we've recycled from years ago, but some of them are quite new and are written in the last year or so. But either way, all of the auto tests are written by humans, and they're written by us thinking of like, okay, what kind of inputs would we need to put into this program to see whether it actually works or not. When you move on from 1511, and even in 1511, this is actually going to start popping up. I mean, some of them have popped up in the assignment already, if anyone's working on the extension stuff. But they're going to start popping up more and more in the labs, where we will put a little note in a lab exercise that says the auto tests are, like, this one's not exactly what you say, but it's going to basically say the auto tests are not sufficient to check whether this program is working or not. You will have to write your own tests. So this is kind of like auto tests are training wheels. So I don't know if anyone... Actually, we don't even use training wheels on bicycles anymore, but I think people know the concept. So back in the day, when people were learning how to ride a bicycle, you'd have these extra wheels on the side of the bike that stop you from tipping over too far. And if they stop you from tipping over too far, then they would help you kind of regain your balance if you start to lose it. Auto tests are like that. They help guide you towards a solution, but eventually the training wheels are taken off the bicycle and the person learns to ride it themselves. So these auto tests are obviously going to disappear at some point in your learning about programming, and you'll reach a point where you have to say, I have an idea about how this program should work, and I should be able to write my own tests to make it work. So we're going to talk a little bit about testing today, and I'm going to teach you ways of testing code that should help in what you're doing, and they may be interesting because they're different from how we would write our code if we assume our code's going to work and we're just building up from scratch. There's a lot of chat going on there. I'm gonna let Joanna deal with the chat there, because I've got stuff to teach here. Obviously, if there's like a lot of discussion going on there, we can actually talk about it after the lecture. I'll stick around as usual for a bit afterwards. So let me move my face out of the way of the text again. Nice point. The compiler can be trusted to understand the language better than us. So if we just write, nearly code, but not quite, and throw it into the compiler will tell us the places in which the code is not structured correctly. So the simplest and first thing that I'll do with any program, assuming that I've put my best effort into writing correct code as it is, I'll throw it into DCC and see what DCC says. There's two types of things that DCC can tell us: errors and warnings. So warnings are the ones that come up in pink in DCC, and errors are the things that come up in red. Not everything's going to come up with those colors. That's if you're running it in a terminal in VLab. But if you're doing it through other ways, you may not get colors. But either way, errors and warnings will be marked as errors and warnings. The error says that the program will not run. So if a compiler comes up against an error, the compiler is unable to make a program out of your code. So the syntax is broken in such a way that the code cannot be built. A warning says, I can build the code around this, but you should know something about it. So the warnings are helpful things for us that say that there's something in our code that we might need to think about that's doing something strange. My advice for using a compiler to try to hunt and correct syntax bugs is always start with the first error. So your compiler is going from the top of your code and going line by line through your code. So it's going through your code from the beginning, and then the first time it hits something that's wrong, that is the first error. I always like to fix the first error, and if you want to, you can actually follow a process where you simply don't look at any errors other than the first. You can look at multiple warnings if you want, but even with warnings, you could be like, let's just look at the first thing. So you could use DCC not as this massive shopping list of issues in your code. You can just look at it as the first thing it says is a genuine issue in my code, and everything else after that could just have been a consequence of that first thing not working. Because that happens a lot, right? So if we look at that simple example of leaving off a semicolon, if you leave off a semicolon, it makes the next line look weird to the compiler. And if the next line looks weird to the compiler, what if that next line was a variable declaration for a variable that gets used like every 5 lines for the rest of the program? Then all of those other errors will appear, but none of them are really the error, because only the first one was, and all the rest of them were just consequences of that. So when we get to that point where we have the errors... Sorry, I'm just getting very distracted. 1 second. I'll be right back. That's what I get working from home. There was someone else having a very, very loud discussion somewhere else. I'm back. So the other thing that we're going to get, and this is something I mentioned earlier, is an error is the result of something going weird. So your compile error might be the first time the compiler notices that a syntax error is there, rather than the actual line at which this is an issue. So the thing that we're going to get with every error or warning that we're going to get in our compiler is, if we know nothing about it, if we can't figure out what the thing is telling us, so a lot of compiler errors are going to have very, very specific programmer speak language going on. The minimum that you're going to get out of this that will help you is that you will know what line the error was on and what character on that line that something happened. So it was like, where in my code, which line, which character, and then at least, if nothing else, if you don't understand the error message, you can at least look there and go, okay, based on what I know about code, and based on me knowing that here is the issue, that something's happening, then you can say, all right, at least I can look there. So the minimum you're going to get is that the compiler will tell you where an issue is. So then if we need to solve compiler issues, we look for where it is, and the first step sometimes is you just look for where it is, and you say, based on what I can see in the code, what is the issue there? And sometimes that's enough. Sometimes all you need to do is have this thing identified. So you can say, my program that's 300 lines long doesn't work, and I don't really know how to look through 300 lines to find something. So sometimes the error message just says it's on this line, and you go, okay, that's easy. If that's not enough, you may need to read the error message and you need to try to interpret what it's saying. So a lot of error messages are going to be reasonably clear. some error messages are going to be very, very unclear. And so it's a matter of looking at that and trying to find out if they do or don't make sense to you. Sometimes the error message will try to tell you that something is there or not there that shouldn't be. So if it's trying to tell you that something's not there that should be there, then we have an issue there, because the compiler may have an expectation of something, but that might not be what you are wanting to do. So yeah. So I'm not sure what's going on in the chat there, but if there are personal arguments or something happening in the chat, can you all just stop for now? Like, you can take it up later or something like that, but we're definitely not going to have arguments, especially if they're not based on what I'm talking about right now. And if you want to, you can just ask Joanna for answers to questions and things. But I think if we're going to be fighting each other in chat about something, I'm sure that there's just some kind of misunderstanding that we should probably work out, rather than like and chat during the lecture is not really the place for it. So let's take that out and deal with it elsewhere, please. Thank you. I don't even know what's going on because I didn't read it all. I'm only seeing the results of it there. Okay. So what we want to do now is I want to show an example here of us looking at some code that has some bugs in it. And this is one of my favorite memes for this course. Poor Grumpy Cat. May you rest in peace. This happens a lot where we have a certain number of bugs in our code, and this is why counting the number of bugs is a dangerous thing to do. So you have like a certain number of bugs, and then you fix a bug, and then you end up with more bugs. But often that means that what's happening is that getting more of your code to work allows more of it to reach other bugs. So if your code doesn't work, it's really hard to reach bugs. But if your code does work, you can reach bugs further in your program and find out more about it. So I'm going to talk about this code, but what I'm going to use is the he's behind you rule. So a lot of the bugs in this code, you can actually just see the bugs and try to fix them. But I'm not actually worried about whether we can fix the bugs or not in the code I'm about to show you. What I'm going to teach you is the process for finding the solution to the bugs, rather than the need to just immediately find them. So we're going to have a look at this code that I have written. I was playing around with it a lot, so hopefully it's in the state that I want it to be, because what I had to do was build this program as if it worked, and then bug it. So I had to put certain bugs in it so that the process of debugging this takes us through the steps in the right order. So let's have a look at it. It's called debugthis.c. Hang on, let me just give you the link. We're in lecture 9, aren't we? Yes. Okay, I'm going to put this link in chat. There. If you are not live with us at the moment, then this is the link here. Hopefully, I'm not sure if you're going to be able to see it, but you know, it's the same link. It's in the lectures, in the lecture section on the course website as well. Okay, public HTML, and it's in lecture 9. Okay, and I'll open this. Now remember for chat, the rule is, if you see the bug, say he's behind you, but don't say what the bug is, because what we're going to do is we're going to reveal this as we go along. So this is some code that is intended to loop and will draw a square of asterisks based on the user input. So we're getting this kind of thing: enter the size of the grid, And if it's a 0, you exit, I guess. It looks like that. And it's looping multiple times, which means it looks like it's drawing multiple grids. So every time you loop, it's drawing another grid. It looks like it's got rows and columns, 2 while loops, drawing stars, and end of the line, etc. And it says, thank you for using grid draw, have a nice day. Okay, so we've got this. Everyone's like, he's behind you. Okay, I do understand that there are definitely issues with this. So, I understand that you can see the issue just by looking at the code. But what I'm teaching you today is not whether you can just find the issue by looking at the code, but a more important skill is that no one will ever get through a programming career by just looking at their code and being able to solve all the problems. The more complex code we write, the harder it is to see these issues. And so what we want to do is, instead of just going, oh, there's the issue, let's pick up on it, we want to go through the process needed to solve these issues. So we're going to look at this code and say, okay, this code's at a certain level of completion. The first thing we want to do is try to compile it. I'm just going to call it debug, and I'm going to say, I'm going to let my compiler find the first problem for me. There are several problems here. I'm going to scroll back up, and as I said, I'm only going to look at the first problem, because I don't know if any of the other warnings or errors in this code are issues. Warning, using the result of an assignment as a condition without parentheses. I mean, without parentheses, not super important to me here, but what I'm getting, if I look at this piece of code, while exit equals 0. So I'm hoping that this was one of the first things that everyone said when they said, he's behind you, is that assigning a value, so this is giving the value 0 to exit, is not the same as asking whether exit is 0. In which case, this while loop might never end. Because we've never really talked about this. Like, what does this equate to? Does exit equal 0 equate to 0? Or does it equate to 1 and stuff? So, we actually, if we wanted to, we could check this. So we could do something like int x equals exit equals 0. So we could just say something like, does this make sense? Like, does this even have a value or not? It actually does, by the way. As far as I remember, if the number is assigned successfully to the variable, this thing will equal 1. It'll equal true if it was able to work. But I don't remember that for certain because I don't use the value of assignments because it's a dangerous thing to use. So we know that's a dangerous thing to use. We know that's something we probably shouldn't be doing. And we also know the intention of this was like, this is obviously a sentinel variable. So it's just checking. So we go, okay, let's check that. Now note that at this point in the process, I am not going to go through and look at these other issues because I'm not sure if any of these other things are what I'm looking at. So this is how I do my debugging. I do one thing at a time. I find that one error, I do what I think is going to fix it, and I test whether it was fixed or not. So we want to be able to have this process where once you've hit a point where you can't solve your problems in a sense, like where you're going, I can't see the issue, I'm just going to my compiler, then what we want to boil it down to is as simple a process as possible. Run your compiler, read the error message, look at line, it was actually like, I jumped to it, but it was like line 14. So it knew where to look, and I had an idea about how I want to fix it, and then that's it. Now I compile again, right? So we keep the process simple so that we can follow it in times of stress when we're not understanding what's happening. Okay, so I've got that. So what I'm going to do now is I'm going to reset it here. You can also use clear and reset. What I like to do when I'm doing this is now if I scroll up, I'm not going to get the previous compilation. So I'm not going to because it's really easy to scroll back past your last compilation and into the previous one and not know which errors you're looking at. Okay, now I'll compile the program again now that I've edited it. And I say, okay, the first thing's now on line 41. And it's saying error, use of undeclared identifier grid size equals 0. It's like, okay. Line 41, grid size equals 0. Do we have the he's behind you here for this one? This is actually an example of the fact that I've laid out my code well actually shows you why there's a problem here. You may not be able to see it yet, but there's grid size. Grid size equals 0 appears to be inside this loop. So why is this a problem? Use of undeclared identifier. Undeclared means it's a variable name that I haven't made, but it's pretty obvious that I have made it. So, so there's a lot of people are like, he's behind you here. Yeah, so you may have figured this out now. And this one I wanted to show you because it's an example of things that can catch you if you forget the correct rules for brackets and indentation and stuff. And also to show you that the issue's not even with grid size. Grid size is created here and it's being used here, but it didn't actually looking at it doesn't even need to exist, but that's a different issue entirely. The thing that's causing this error, if we look at the idea of it being, so the variable's inside some curly brackets. What goes on inside curly brackets stays inside curly brackets, which means that this variable I'm expecting to still exist here because the closing curly brackets is on the same line as the opening curly brackets. But you can actually see my editor trying to help me there. So see how this bracket is highlighted while I'm next to this bracket? Or I click on this bracket and this bracket is highlighted and it's like, oh, I've got a bracketing issue. And then you can start to see, because of the way I've laid out my code, you can see the bracketing issue. The bracketing issue is there's two closed brackets right above each other without any opening brackets in between. This is not how this works. The thing that's directly above should be like this. There should be something that opened it, so a line that opened the brackets, and vertically below it, with only white space between them, I should see the thing that closed it. And I should never see this closing and then white space and then closing. It means I've laid something out wrong, or I have made a mistake about where I've placed these. So here I have this while loop appears to be well formed, this while loop appears to be well formed, this if statement appears to be well formed, this while loop also appears to be well formed, but if I look carefully at it, I have this, or this bracket, I think, which doesn't appear to be matching up with any open brackets anywhere. So I think that this is a typo. I think that I've added too many brackets in there. So notice that the line that the error was on is not where the error was. The variable referenced in it was not the problem. What I get is an example of an error being a consequence of a syntax error somewhere else in my code. And so these are the kinds of things that you're going to see. And it depends on how you've written your code, how easy or how hard it is to find those particular issues. So I'll save this and compile it again and see if we've got any issues. I'm gonna reset my terminal so I can see my current compilation only. We compiled! Great! If we compiled, there's no problems with our code, right? Submit and never look at it again. No! I mean, obviously, if it's in a lecture, it's not just gonna work like that. Okay, so having said that, it's 12:03, so we'll go on a break, but that was a little glimpse into the process for solving syntax errors. So what we want to do is we want to be a little bit kind of systematic about it sometimes, rather than going, oh, just read the whole code and see what's wrong. What we want to do is we want to compile, look at the first error, look at what might be causing the first error, fix it, ignore all the rest, and compile it again. You know? So that's the simple process if we want to do that, rather than getting caught up in multiple things. Okay, so let me skip to... Oh wait, was this the... Oh yeah. Okay, no, that's fine. I know. I was going to be careful with these particular slides that I don't give away the spoilers. Okay, so this was the spoilers. So there was a single equal if statement, so that was an issue that we had. Oh, yes. Chicken's telling me that I need to go on break. And there's an extra bracket that causes a lot of issues and some weird error messages, right? So that's something that we found. Those were the syntax errors. The next thing that we're going to be looking at is testing, but we're going to go on break first and then do testing afterwards. So just know that before we get into it even, testing is hard. It's not the easiest thing to do. It's a skill that needs to be learned, and it's like learning how to break your programs is very, very difficult. So I've got this funny tweet here from 2018 from, I think it is a QA engineer, a testing engineer. It says, okay, QA engineer walks into a bar, orders a beer, orders 0 beers, orders 99999 beers, orders a lizard, orders -1 beers. This is exactly how QA engineers think. They just go, okay, you made variables. I'm going to give you all the values that you don't think are logically correct for this and make sure that you're handling them correctly. But then, even after all of this testing that we've done, all this care we've put into our programs to make sure they work, first real customer walks in and asks where the bathroom is. The bar bursts into flames, killing everyone. Yeah, so that is the life of trying to make software work really well. And that's why we do want to learn a lot about testing. But we'll do that after the break. It's 12:06 now. And we'll come back at 11 past 12, and we'll continue with that program, which a lot of you have said that the errors are behind me because you've had to play around with this already and seen what the next errors might be. But we're going to talk through the process of learning about those errors after the break. So be back soon. Okay, I'm back. Been keeping you in suspense for the 5-minute break. So, let us think a little bit about testing. I wonder if I should talk about this slide now. I'm keeping you in further suspense. So, testing. We need to actually run our code to see if it runs the way that we want it to run. I hope that is something that people have thought about already and have been doing with their code. The first step is run the code, of course. Run the code. But even if the code appears to be working the first time you run it, that is not a guarantee. Any of you who have, run your code yourselves first, just to see whether it's running, and then auto test it later, may have noticed that the auto test will give you way more information than just running your code will. And you'll be like, you'll pass the first 2 or 3 auto tests, and you'll be like, oh, it works. And then you'll have this massive string of errors from the later auto tests that are testing more interesting possible inputs to your code. This is us writing tests, so we write a sequence of tests which is like, okay, simple things, does it work? If the simple things work, more complicated things, do they work? We would do this when we're just making code. But if we don't have auto tests, which is something that we do need to train for, is not having auto tests, it's just a matter of us trying to figure out the situations that our code will and won't work in. So, first of all, let's go and do the basics on this. Let's do some testing. So we've got our code here, and our code is now compiled. If it's compiled, it must work, right? Sorry, I apologize. You can tell by my laughter that the code's not necessarily just gonna work. I just realized that I'm covering up a bunch of the code with my face, so I'll just move that across over there. Okay, so let's run it. Obviously, everything's going to be fine, yeah? Chickens just come to tell me that things may not be fine. Oh, look, it's totally working. Enter the size of the grid you would like to make. If you would like to exit, please type 0. So I'm not going to bother testing the exit condition right now, because I just want to see this thing working. So give me a 5x5 grid of asterisks, please. See? It's totally working. There's definitely a 5x5 grid of asterisks being printed somewhere here. So I don't have a problem. Everything's fine. No worries. Everything's good. I'm going to press Control-C because I obviously have a loop that's going forever. Control-C at least in DCC compiled programs is actually going to tell us something. So we actually get what is very similar to a compiler error here that says line 32 in debug this. Here we're in this printf statement. So this is the one that's going forever. Although considering it's the only printf statement printing stars, we kind of know this already. And as people are saying in chat, yes, there were 5x5s. There were many 5x5s, and it looks fine. So yes, there's an issue here. We wanted exactly one 5x5, and then we wanted it to ask us to type in another number for more. So what I'm going to show you is I'm not going to show you exactly what the problem is, because that's not what we're looking at here. I'm going to show you ways that we can try to solve this problem. Because what we have is a situation where we've got a loop that's going forever, but we need to figure out why. So the trick here is not just look at it and find the answer. The trick here is to rewrite parts of our program so that we can get the most amount of useful information out of this. So what I'm going to do, this is like the kind of basic level of testing. As you get more advanced into programming, you're probably going to debug your logical errors in slightly different ways than this. We're going to give you this one for now because this one is quite a good way to get started on these things. So what we're going to do is we're going to ask ourselves, what is the current state of the loop? And given the current state of the loop, we're going to learn what that current state is so we can see what's happening when we're in this infinite loop and find out what's going wrong. So I know that many of you can see what's going on here. Many of you can just look at this and see what the problem is. But again, what I'm trying to teach you is not to just magically be able to see the answers when you look at something, but to have a process for the times when you can't figure it out. I just have to keep the example simple for the lecture because I don't have enough time to give you a real debugging problem. Like, I've had things that just sort of sat in my code for like a month, you know, and you go back every day going, I know that bug still exists in here, but I can't figure out exactly where it is. So I'm working on other parts of it, you know. Sometimes I'm narrowing it down and stuff, but sometimes it's just not coming. So it's like, it's like that. So what I'm trying to teach you is for those situations, this is how we get more information. So I know that there's two variables for these loops, and the variables are in the decisions of whether we're doing stuff in the loops or not. So if the variables in those decisions, we need to know what those variables are. So this is like exactly the way I would do this a lot of the time. Okay, this should give me some information. So what I've done is I've written a print statement that runs every time the outer loop runs. So the outer loop is saying the row is this, the column is this, and stuff. And I know that this print was happening multiple times, so maybe I want information on the inner loop as well. So what I want to show you is this process, you know. I don't mind whether you can or can't find out exactly what's going on, but what I want is a really nice kind of like, this will give us some more information to be able to tell maybe what's going on. So simple print statements. I'm going to say that this works for now. So you just got to be careful. Print statement debugging works very, very well for a lot of the stuff we're doing in COMP1511. By the time you get to like sort of third year programming, you won't even use these anymore. You'll be using something else. But for now, this does work. Okay, so I save that, and note that what I'm doing is I'm writing code that specifically is not doing what my program's supposed to do. Because if I was to run this and it worked correctly, I'd have all these print statements happening in between these stars that I'm trying to print out. So these print statements literally would cause a working program to fail something like auto tests and things. But the point is not at this point writing code that works. It's about writing code that gives us enough information to find out what's not working. So a lot of the times you have to kind of like, you've got to open it up and look at the information rather than trying to stick to only writing code that is like 100% perfectly correct. So these things are lines that are not part of the correct code, but they're going to lead us to the issues that we're having. So we're going to compile that again and run it. And obviously I haven't fixed the loop. It's still an infinite loop, but what I need to do is see what's going on and see what my problem is. So let's go with for 5 again. We know that no matter what number we put in here, it's going to end up going to the infinite loop. But this time when I stop it, I can read the lines that are being printed out and it will give us information about which of these loops is going forever and how. Okay, so I'm going to stop that there. It stops in the same place, well, roughly the same place. It's a different printf now because I introduced a printf here. And it looks like I'm scrolling up. You can see my scroll bar there moving. I'm not going to go any further than that because it looks like this line's repeated again and again and again. I mean, as long as it's repeated more than 5 times, I know that this one is the infinite loop. So, in a loop, row is 1, column is 0. Row is 1, column is 0. Column is 0. Column is less than equal to grid size, column is 0. That's the issue. So column is 0 and it's not changing. Now, many of you will probably have seen this already because it's right here that I have iterated incorrectly where I've set row to be equal to column plus 1 instead of this being the column loop here should have been increasing column, not row. So if column's the variable that needs to change, it needs to change. And if I want to make this less likely to fail when there's only one variable being referred to, I do column plus plus. So everything's fine now, right? Everything's working, and there's no possible issues in this. Sorry, you know that there are. Okay, but we need to find them. We need to get our process right so that we know how to find them. So this is another reason why I would do stuff like column plus plus, because you're less likely to make an error if there's only one variable involved in the increment. Okay, so I'm going to fix that, and now I will not have any problems with this. So I fixed it, I've recompiled it and run it. So now it will obviously just do the 5x5 grid without any issues. Oh. Uh-oh. This appears to be another infinite loop. Row is 0, column is 6. Column is 6, so if it's 5 and it gets up to 6, then that's probably fine. It's done its line, but the row is equal to 0. That's fine. But is it? Is it fine? This appears to be ending the row, and then this is incrementing row, which should happen at the end of this while loop. Oh, I got rid of the wrong bracket, didn't I? When I was fixing those two brackets, so I fixed the syntax error, that's fine. I got that working, but obviously I've created another issue here where I closed the bracket too early. So, let's try that. And maybe now row, I'm just going to change this. Now that I have changed the format of my incrementers, I will try to keep them consistent. Keeping things in the same consistent format makes it easier visually to see where the incrementer is. Okay, so now the row will be going up, so we're not going to get that infinite loop there. I'm going to go out on a limb and try removing these printf statements now and see if my grid prints, because I think I've got it now. He's still behind you. We'll see. We'll see. James is saying, this is like an unsatisfying video where they mess up on purpose. This is exactly what I'm doing. Okay, so I fixed another problem, I test. Now, note that for those of you that can see multiple problems happening at once, be careful of trying to fix too many at once. The more problems you try to fix at the same amount of time, the more chance you have of not knowing whether your solution worked or not, right? So heaps of times where people debug things, they go through and they change like 8 different lines, and then they run it, and something starts working, but something else stops working, and you're not really sure which thing you've done that works or not. So this is why I keep jumping back into compiling and rerunning this while only changing one thing at a time, even though both myself and several people there can see what the problems are. There are other problems here. I'm fixing just one at a time, and I think it's important to do that because then you've kept track of what's going on. Okay, grid of 5. I have 6 stars here and a bunch of blank lines, but then I go again, which is good, right? 7. It appears to be trying to create the grid. So there's something going on here which is closer to correct. We can see ourselves inching towards the solution. I mean, one of the first issues we've got here is there's 6 stars here for the 5, and there's 8 stars there for the 7. So we could look at that. Our row is one too long. If our row is one too long, we look at the while loop that is creating the row, and we go less than or equal to, less than or equal to. And this is why a lot of the time when we make our while loops, we make them exactly the same format. We start at 0, we go to less than the size, we'll get exactly the right amount. You know, if you jump around between less than or equal to starting at 1 and stuff like that, you're less likely to notice this issue. But if you format all your while loops exactly the same way, this less than or equal to stands out like a sore thumb. You look at it and you go, why is that one different? Because that one's different from the standard setup. If it's different from the standard setup, then we need to look at it and find out exactly what's going on. And we can see that that's an issue. So column 0, column less than grid size should get us the right number there. So let's save this and make sure that that change has made a difference. I have to press 0 to exit. I hope that works. I haven't tested it yet. Okay, thank you for using Grid Drawer. Have a nice day. Thank you. I will have a nice day. I'm lecturing today. It's always fun. Okay, so we're going to debug, compile that, run it again. We've got 5. So we have 5, and we have 1, 2, 3, 4, 5 lines. So this is actually nearly working, but we're not getting all the rest of these lines, so something else must be happening. And we look at it, and this is where, like, you know, just all these little things are going to cause issues. I should probably speed this up and go through. I have other things to talk about today, but the things that I want to get through and I want to get clear to everyone is one problem at a time. So I did that with the syntax errors, where I said I will fix the first error only, and I will literally ignore the rest. I literally did not read the rest of the errors, because one at a time is enough to get what we're doing. And then when we're testing, if we don't have enough information, it's hard to know what's going wrong. So what we can do is we can add lines of code in here to tell us what's going wrong, and we'll get more information. I'm actually thinking of turning these back on now to see what my problems are here and why these lines aren't drawing. So I will compile this and run it again and test. Did I not save that? I didn't save it. You're gonna save the file before you compile it. 0. Okay. Compile and run. And now we get some information, and now it's easier to see it because we don't have an infinite loop now, so you can see it. So outer loop, row 0, column is 0. Inner loop, row 0, column is 0. Inner loop, column counts up to 4. Outer loop, row is 1. So we've gone to the next row. Column is 5. Oh no, column is 5. Column is 5, column is 5, column is 5. So column starts at 0 and counts up to 4. And then we go, okay, so we've got an issue here that the column is staying at 5 through the extra rows. And so we can go, what is happening with column, right? So immediately, so that issue there, that last issue, some people would have been able to see it, some people won't be able to see it. If you couldn't see it, now that I put these printf statements in here, it should be clear to see it. So hopefully what I've shown you is that getting more information about what's going on is super valuable, right? And so if we have more information about it, we know what's happening is that the column variable is the issue. It's starting the next line as 5 rather than 0. And we need to think about, why is that happening? So column gets set up here as 0. First time it goes through, it gets iterated up to 5, and then we go back to the next row. Because column was a persistent variable outside of both while loops, it keeps its value through multiple runs. And this is why there's a little kind of like convention for how we do things sometimes, where we like to say that our variables should be declared as late as possible before they should be used. So if we're going to declare our variable as late as possible before it can be used, it should be just before this line. Oh wait, I need that. But this is my printf statement. It's not part of the program itself. But even so, even if I want it for there, I can put my column here, and there's a fundamental difference from where it was a second ago to where it is now. Again, you can see I'm only changing one line at a time. I'm just moving one line, and I'm going to test this again. But this is now inside this loop. So when we go to the next row, the column that we used previously, the variable column, will disappear. We go back into this loop and we start again. We create a new one. So we're creating a new one at 0 each time. That should start at 0 and then go through. So actually, I'm not going to delete the print statements yet. Let's run this again and see if it is getting reset and counting. This is much better. Row 0, column 0 through to 4. Row 1, column 0 through to 4. Row 2, column 0 through to 4, etc., etc. This is getting closer to what I think ought to work. And so now that I know that my printfs have given me the information I needed, I'm going to comment them out so that they're not going to be used, and I'm going to run this again. we got there. I'm not 100% sure that this works, but it works for a simple example now. So, not bad. Negative 99 didn't run at all. That's good. That's not valid. And there's lots of maybe other things that I'd want to test, right? So maybe I want to put a really large number in. I don't even know what's going to happen. My terminal probably won't be able to handle this. Yeah, so it has potentially worked. I don't know because I can't see it clearly. Oh, what happens if I do 1? Hey, 1 still works as well. What about 0? Oh, no, 0 is the exit. Yeah, so I think that a lot of things are working at this point. At this point, I'd be able to say, okay, I think this thing's working now. But what's more important is how did we get here? Oh, by the way, don't leave these things in. If your code is finished and you've solved the problems, don't leave a comment which is like just a running line of code that happens to have been removed. Because people are going to read these looking for information. So this thing's obviously good. For each row, loop through the columns, loop through the rows of the grid. This is not a useful comment, and it muddies the waters because people are going to attempt to read it because it's color-coded. So the only reason I was commenting and uncommenting it was because I thought I was still going to use it. If I don't need that testing anymore, then I'll remove it. Because what it's doing is it's drawing people's attention towards something to read it because it seems to have information. Okay. That's my program as it is. I'm going to leave it like that, so it will be in the live lecture code now. You can see the finish, but I think what's more important than the finish here is the process that we took to solve it. So back to our slides. We're testing to make sure something's working. So when we run the code, we do look at different inputs, but it's not just inputs that we're doing. We use our output to show what's happening. So this is more than just the final output of the program. We'll use our output to tell us things about the current state of the program in particular parts of it. If you can pick apart the current state of the program, you will be able to see at different points in time what the progress was of the program. So you just go, all right, what does your memory look like at this point? So sometimes there's only parts of the memory we want to look at, certain variables. We'll ask the program what's happening with its variables at certain points in time, and then we get more information. As you get more advanced in computer science, we will show you other things where you can actually pause your program mid-flight and read what the variables are doing, and you can just step through from one line to the next and go, okay, what's our program state at this line and this line? But we're not doing that in 1511 because they're just complicated enough that they're real fiddly to learn at the very beginning. So we're going to keep it simple and go, okay, we can do this kind of thing where we can find out where in the loops we're at. What are our iterators doing? Are they working correctly? I mean, loops are really one of the places where you're going to see the most problems. But once we start working in weird data structures, you're going to see more problems like that. So Coffeen is just saying they left a printf like that in their draw X. So it's sort of okay, but you can see how leaving enough of those commented out printfs in is going to leave people, like, it's going to get people to try to read them in a sense. And if they have no information about what's no human information for what's going on, they're not that helpful. So hopefully that tells you. So the principles that we're trying to get to is test one thing at a time. Fix one thing at a time. Make sure your fix is working before you move on to the next. So it's a simple process. That doesn't mean it's easy. It's just simple. The difference between them is like simple has less steps to do, but that doesn't mean it's like it doesn't require skill. So I think this is what I was talking about already. You can write your program to give you information. And every time you test something, decide what it is you're trying to find out. So with what we were doing there, it wasn't too hard because it was like we could see our problems. But you could see sometimes when there was more than one problem, how I said, I'm just going to pick one of these. So I had a situation where it was like too many asterisks and a lot of blank lines. And then I just said, no. I'm just going to look at the too many asterisks. I'm going to solve that one first and then keep going. The printf statements in our code are pretty handy because the same thing I was saying, it's like this thing, the needle in the haystack. If you can break the haystack into parts, much easier to see what's going on. So the haystack is all of our code. So say I've got 10,000 lines of code. I've got a pretty big program. And I know that something's wrong in it. If I start putting those printf statements out, I will be able to see which parts of my code work and which parts of my code don't. And then you go, okay, it's not 10,000 anymore. It's like 100 lines of code. And you go, okay, take out all those other printfs, don't need them. Go into this 100 lines of code and go, okay, detail in here. And then you go, okay, there's 10 lines of code. And then you go and actually read that code and you say, okay, now I know that in these 10 lines of code that something's happening. Then you go deeper and you find those issues. So a lot of this stuff is really handy, and I think that the most important thing when we're thinking about debugging, when we're thinking about trying to fix our code, is you're usually not in a debugging mindset until everything's gone wrong. And when everything's gone wrong, then what you do is you say, I need something to dig myself out of this mental situation where I can't deal with it. And really, that's like one of the most difficult things with humans is once we dig holes for ourselves, we're very, very bad at climbing out of them. And the easiest way to do that is to say, I'm going to rely on a process. So I'll go back, and you can have this written on the wall next to you. I mean, I guarantee that if you have this kind of debugging process written on the wall next to you, don't write on your wall. Maybe write on a piece of paper and stick it on the wall. When you're doing your assignments and your exam and stuff like that, this will save you time. Because anytime you get stuck, you'll be like, all right, go to the first compiler error, go to the line of code, read that, see if that's the issue. If that's not the issue, look above it for consequences that might lead it to being the issue. Fix that one and only that one, and then repeat. You know, you can get it to a process where your confused brain at that point, or your tired brain at that point, doesn't have to do any work. You just follow the instructions and let it happen. So that's the thing, and if you can do that, a lot of the easier ones will fall away. The harder ones are like, you know, go find a whiteboard, spend 2 hours on that, working on the theory, and then come back and do it again. But those are bigger problems. Okay, so I think these are all the slides that I just worked through. Yes. Yeah, okay, so we can have this line here. Try outputting row and column values to make sure they're working. So we've already done this. So this is the steps. These slides are stepping through everything that we've just done. Try outputting loop information. So I said inner loop, outer loop, that kind of thing, so we can see what's happening. Okay, so let's move on to the next thing that I want to talk about is characters. So up until this point, we've had ints and doubles as our basic variable types. So those variables that store an individual value in them, ints and doubles, but now we have characters. We have other variables because we've used both arrays and pointers, which are kind of like meta variables. They're variables that the value that they store themselves is not quite as important as the thing that they're containing or aiming at. So the array is there to store multiple of these basic variables. The pointer is there to give you access, remote access to one of these other variables. And so this is a basic variable type called a character. I was about to call it a char. We call it char sometimes for fun because that is the shorthand name for it. So int and double are variable types. Char is a new variable type. And it stores characters. So we can store the letters like A, B, C. But the funny thing about it is we can also store the numbers 0, 1, and 2. We can store a whole bunch of things. And they're actually 8-bit integers. So these are the smallest variable types that we're going to be working with in this course. And the funny thing about them is they're not encoded as characters. So they're still zeros and ones. And the zeros and ones are stored in exactly the same format as an integer. So the character is actually an 8-bit integer, but because it's 8-bit, it has a much smaller range than the 32-bit integers that we were using. And it also doesn't have negative numbers. So it actually goes from 0 to a theoretical value from between 0 and 255. The way that relates to numbers is through this system called ASCII. ASCII is like the short for, and I had to look this up because I've always just called it ASCII and never really looked it up, the American Standard Code for Information Interchange. The funny thing about this is actually designed originally for keyboards. So the way that ASCII worked was our keyboards would, whenever we pressed a key, send a signal to our computer, and the signal that got sent to the computer was an 8-bit number, because there were just enough keys on the keyboard to require an 8-bit number to represent each different key. And the basic ASCII that we use is just, I think, 0 to 127. That is for every key. And the interesting thing about this is we're actually not going to be using the char variable for individual characters. We're actually going to usually be using integers for them. I'll show you why in a second. But we will definitely be using character arrays. They're called strings, and we're going to look at them on Friday, actually. So, you don't need to memorize the ASCII table. So don't worry about that. Like, people often look at it and go, oh, I need to know what the numbers are for these things. You can actually technically never use the numbers in the ASCII table. You don't have to memorize any of them. But it's nice to know that all of the characters are numbers, because then we can use them as kind of relationships between each other. So you have something funny, like the difference between A and B is 1. So if I take an A and I add 1 to the A, it becomes B. So there are some little things like that, but what I want to say is, like, you don't have to memorize the ASCII table. You actually don't even need to look it up. We provide it as a well, actually, we don't do secret exams. We used to provide it in exams, just because people were comforted by being able to look at ASCII, but you never actually need it. So I'm going to say, like, I'm not going to give you a massive table of things to memorize. That's not what we do here. But it's nice to know that they're numbers. And the other thing that's interesting about ASCII is it's not just upper or lowercase letters. There's the digits. There's the punctuation symbols. So, like a hash or a dot or any of the brackets that we have. The space and the new line are also ASCII codes, in the same way that if they're on the keyboard, they would send some information to the computer. So they're keys that you can press on the keyboard, and they're actually characters that can be printed out, because we can print out a space and a new line, so they also have values. So, learning how to use these in code, we have, I'll show you in a second why this is like this. We use an integer often to have an individual character. For us to want to store the value of a character, we're now going to be using these single quotes. So when we use double quotes like this, what we're saying is there's a bunch of characters. And this is actually the format we're going to use later for even working with arrays of characters. The double quotes we've been using a lot. The single quote says, I am one character only. And if I'm one character only, then I have a number value that can be stored in a variable like an integer. So I can store the value of A in an integer. I think it's 97? Is that upper or lowercase a? I have accidentally memorized some of the ASCII table without trying to. So we can store the number value of A in a number variable. So we could have stored it in a char variable here, but for reasons I'm going to show you, we're actually going to be storing most individual characters in integer variables. And so I can say, I can print out, and now we have a new symbol for our printf to print out a single character. We can print out the letter C has the ASCII value of this, and these are the same variable. This is the interesting thing. So if I say, look at it like it's a character, then my printf is going to say, I will interpret the number that you've given me. It's an integer, right? I will interpret that number as if it's a letter. I will look up the ASCII table and I'll show you the letter. If you say, I would like to interpret this integer, it is still an integer, as a number, it will tell you the number. So let's run this code. Because I have... I thought I did. Hang on. ls. I do have a char demo, yes. Char demo, there we go. Okay, so we've got this much. I'm going to just comment out the rest of the program here, so we can just see this one bit happening. So we've got the letter A, and I'm going to say this will print it out as the letter A, this will print it out as a number. So we've compiled that and we'll run it. And this shows us, oh, I was right, it was 97. The letter lowercase a has the ASCII value 97. So these are in certain ways interchangeable because they're both the values of this variable. Note that the same variable interpreted in different ways, because the variable is just storing a bunch of zeros and ones, but if we interpret it in different ways, it has different capabilities. So if I say, look at this like it's a character, if the number is low enough to be a character, so it's going to be like 97 there, I think that the ASCII values are only 0 to 127, then it will be able to interpret it and say, okay, this can be shown as a character. And then if I want to look at its number value, it will be whatever its ASCII code is. You don't even have to memorize these ASCII codes, because anytime you need it, you notice I never typed in the number 97 here in my code. I just use the letter. So you can just use these letters and find out what their values are if you ever need them. There are a lot of really helpful library functions that what are you talking about? Oh, people are talking about logic programming stuff. I think there's some really good logic programming stuff in discrete maths at UNSW. Anyway, we're going to use libraries, and getchar is a function that's actually from the standard input-output library. So this has been available to you since the very first week of the course, but we've been using scanf and printf for everything. And one of the issues that we're going to get with scanf, and you know this if you've been using it, is that it automatically, if you type in, say, numbers, is going to use a sequence of numbers and go, I'm going to take them all in as one number. If you put spaces in with scanf is going to ignore them. So if we wanted to really, really carefully grab all of the letters that are typed in standard input, including spaces and new lines and things like that, we might want to get one character at a time. So getchar is going to do that for us. So it's going to say, I will read 1 byte from standard. 1 byte is one integer between 0 and 255, and we'll say that's likely to have an ASCII code, but we don't really mind if it does or doesn't have an ASCII code. What it will do is it will say, I'm going to read 1 letter, basically, and getchar will put that letter into a variable for you. So basically, if you look at the code here, I'll uncomment this now so you can see it. Getchar, I can have an input character there, and I can run getchar. So getchar would say, user is going to type in something, and it will be stored in this integer here. And now we get to the reason why that's an integer. So getchar can return a -1. So if it returns a -1, it's saying end of file. So we've danced around the idea of EOF a little bit when we were talking about scanf before, but we never used it explicitly. EOF is actually a hash define, and it's in standard input output. I think it's also in standard library. It's in a few different places. But what this says is that there is some way that my user can tell me that the input is finished. When we're working in a terminal, the way that we say we're not going to give any more input is we press Control D in the terminal. But it is called EOF because it's end of file. When you get to a certain point where you start actually reading information from files, we're not doing that in 1511, but you will eventually get there. When the data in the file ends and there's no more information in the file, EOF will automatically be sent in. Actually, when I think about it, we are doing stuff from files. Because we've given you the option to work with test files in the assignment. So you can say, take the information from this test file and use it as input into your program. When we get to the end of the lines of text in that file, which are just input lines that you may have created, EOF will automatically be sent to your input. And so when you're working with scanf, you're just checking whether you got valid input or not. So you're mostly just checking for, did I read a number? And if I didn't read a number, then there's an issue. EOF says not a number to you. It just sends not a number is actually a keyword for something else, but it sends EOF when it's done. And we can do it in terminal by pressing Control D. Getchar will give us a -1 where that happens. Now, the char is not able to represent -1. So if we give -1 to a char, it's going to go 0 less than 1 from 0 is actually 254. It's going to integer underflow from 0 back to the top of the values and start counting downwards again. So it's not that safe to use, because that potentially is a character. So that's why we use integers. So if we see the -1 from the get char, then we know that the input is finished and we're not going to take any more. The other thing that we need to know when we're using get char is it won't grab the characters one at a time. It'll wait until the user has confirmed the input and sent it through. So I could type in a whole bunch of characters and nothing happens in the program until I press enter. When I press enter, the program reads all of those characters and says, okay, I have what's called a buffer of all these characters that are written, and this is the first thing in the buffer. So getChar will look at the first thing in the buffer, and if you're looping it, it will then go through the buffer and will grab the letters one at a time. But it is important to note that we can't just tap the letter and have getChar do something. So people were talking about, when I was doing the tourist, people were asking about, can we do this stuff in real time or not? There are other ways to do it, but not exactly here with getChar. getChar has an opposite function. It's called putChar. So this is the thing that says, oh, I'm not reading something from the user. I am now giving something to the user. So this is actually, I don't want to say it's the same, because I'm sure that there are some subtleties that make these different. But putChar, and if you give it a character, is going to do basically the same thing as printf, flag for a single character, and then the character. But I don't want to say they're exactly the same, because I know there must be some subtlety in these that makes them fundamentally different. But you can think of it like this when you're learning how to use it, for sure. So using both of these, we can read a single character by saying set up the input. I've showed you this code already. We'll run it in a second, and then we say getChar like that, and then this is just a printf that gives us some information about it. But then what we could do is we could just write that character back out to standard output if we want to. We call these standard input and output. Anything that reads or writes to the terminal we call standard input, standard output. Okay, so I'm going to comment out this first section, which was the first demo, and then we'll look at this section here. I might comment out the section down here that we're not using as well. So I'll save that, compile it, and run it. So we're on this line here. Please enter a character. The program cannot continue until at least I press enter. So the getChar is there. So, okay. Let's character C, because we're going to give C to C. And so I'm guessing that the ASCII value for C is 99 because it's A, B, and C. But we'll see. The input C has the ASCII value 99. So it was able to read it in using getChar. It's telling us that. And then we used putChar to print out a character. I could have used putChar here, actually. I'm going to, just for fun. I could putChar the new line character here as well, which was done in the printf there. So this shows us that we can read a single character and we can write a single character. I mean, this nearly is simpler than what you've been doing with printf and scanf, but it can be used for different purposes. The other interesting thing about this is there are ASCII codes for the characters we can't see. There's EOF as well, which is the same thing as Control D when we use it. Sorry, clicked on that by accident. So when we do getChar, we can actually capture these characters. So if I just looped getChar for ages and picked up a whole lot of characters, I would then pick up all the spaces as well as all the new lines and things in a way that scanf doesn't generally do. And an interesting question there is like, what do you use putChar for? And it is an interesting question because technically you could just use printf for everything. Often the only things we're going to use putChar for is where we're looking at just individual characters being placed in a very particular way, and you want to not necessarily have all the printf code going, but also maybe you want the code as you read it to look different for single characters as it looks for large sections of characters. So when people look at it, they go, oh, putchar, this. Whereas printf, we're expecting this whole chunk of code, chunk of text to end up appearing. But really, not a huge difference between this and using putchar. I wonder if we should... No, I'm running out of time. We'll look at working with multiple characters, and then we'll show the invisible characters at the same time there. I'm going to demo all of this on Friday anyway in an actual program, so don't worry if I'm not showing everything right now. So we can read in multiple characters using this thing like a read char, and we're actually using the result of the get char to see whether we should keep looping or not. So this will read characters in until the input finishes. So the input finishes either with a Control D or a or if it was reading from a file or something like that, it gets no more input. So what we're doing is we're looping here, and the sentinel variable is actually the character that got read. So the number for the character that got read, getChar is run on that character the first time to see whether it's a valid character. It's a valid character if it is not an ender file. If it's not an ender file, it's valid, and I can say, I read this particular character, ASCII. So this is that same printf I've been using. And then my iterator for this loop, so it's actually a slightly different loop than before, used to run the getChar function again. This gets the next character from input, and it comes up here and says, if this was a valid character, I can continue working. Let's have a look at this loop in action. I've got just enough time to show this before we wrap up. So I'll comment out the rest of my program there so that we're only running this multiple characters loop. Type in multiple characters ending with Control D to stop. So I could do A again. I read A with ASCII code 97, and then you're like, hang on, what's going on here? I just typed A and enter. But I typed A and enter, and I got 2 lines saying I read a character. So I read a character A with the ASCII code 97. That's exactly what we expected, because we've been working with A earlier. We know the ASCII value of... Oh, I typed it differently. One says ASCII value, ASCII code. It's the same thing, right? 97. But then there's another one, and look what it did. It split the line, because what it's actually showing us here is an invisible character that has an effect, which is actually the new line character. And the new line character here is going to put this down on the next line instead of actually printing out the character. So I read character new lines, and the new line's actually there. But we had to use a special code when we were trying to type in new lines. When it's going onto the terminal, it actually just does an enter. So it says, I read the character, enter key. I mean, it was the enter key when I pressed it. And it has an ASCII code 10. So now we know that the new line character is actually represented by an ASCII code. So I could do more of this, and I can say, hello there, and it says HELLO, and it's got all the ASCII codes for those. And then I've got this one here, the empty space, which is the spacebar. The spacebar also has an ASCII code. So now we can identify that there are a lot more characters than just the letters. I'll show you something funny as well. So I've got my space there that has a code, I've got my enter again that has a code, and I have the numbers 1, 2, 3, 4, which have the ASCII codes 49, 50, 51, 52. So, gotta be careful with this. If you type in numbers and store them in characters, they will not have their number value. So the early ASCII codes, the 1, 2, 3, 4, the numbers 0 through to 9, the ASCII codes 0 through to 9 are used for specific purposes. So they're used for specific functions on the keyboard. I can't remember exactly what they are. But your numbers are not necessarily going to end up numbers if you're reading them in as characters. So you've got to be careful. There are ways to convert numbers to and from characters. Okay. There are more character functions, and ctype.h is a very useful library to work with character functions. You can figure out if something is an alphabet, a number. You can convert things between lower and uppercase and things like that. So I'm going to wrap it up there. We will be looking more at characters on Friday. We will start to put them in arrays, and we start to look at strings, and we're going to do some demos there. There's not that much. It's not really worth demoing individual characters as much as it's worth demoing words, because we as humans prefer to use characters as words. But today we looked at debugging mostly. I mean, it was a recap of pointers as well, and characters. So I'm going to wrap it up there. That's actually probably one of the least code constructing lectures that we've got in the course. But I think it's still very important, because debugging and the process for actually removing errors from code is potentially more important than being able to write code itself. So we're going to wrap it up there. Don't worry if characters are a little bit confusing now. We will definitely be looking at them again on Friday and going into a deeper demo there. So I will go into be right back mode, and I'll come back in a second and stick around and answer questions if anyone has any. Thank you all. See you soon. Alrighty, I'm back. Not sure if there are going to be a lot of questions today, because I think that what we were doing wasn't necessarily like, really heavy C syntax or anything like that people need to ask questions about. But I'm here anyway, so if anyone has any questions, throw them in chat now, and I'll see if I can help you. Dinyanda is saying, is the ASCII value for new line being shown because we pressed enter, or is it because of the new line in the code? Let's go back and have a look. So when I type in something like this, I typed in A and enter. Then let's have a look at what the loop will do. Read character, read char, is that integer, and it gets a value from get char. So get char says, when the person types in characters and press enter, then they all get stored kind of in the terminal's buffer, saying, okay, these are the things that the user is trying to give to you, to the program. And the program says, okay, I'll read one of them. So it reads the A, and then it comes in here and it prints this out saying what the A is. So that's the basic stuff that we did before. And then it says read another character using getChar and store it in the same variable. So what's actually happening is the buffer of all the keys that I've pressed that are getting sent to the program has the enter key in it. So even though the enter key is the trigger for the characters getting sent to the program, it is also a character itself, and it's the program's not going to leave any characters out when it uses something like getchar. So the next thing that goes in is actually the enter key. So at this point, the second getchar reads the enter key, and it comes back to the start of the while loop, and it says the enter key is not the end of input. So I read this character, and it will say I read this enter, and it goes down to the new line because this basically gets replaced with that. So when the read char is value 10, this character, instead of printing out a visible character, prints out this invisible character, which still has an effect. As you can see here, still has its effect. And then it says what its ASCII code was. I should also point out that at this point, I can press Control D. And that was me pressing Control D. And all that did, Control D, meant the next character that was read in could not read a character. So it gets end of file, and it comes here, and it says read char is EOF, a hash defined EOF, so it will just leave. So I actually didn't show that during the lecture. Yeah. Hussein's asking, does C have a get string, or do you need to store get chars as an array? We will definitely be using get chars in loops for arrays. Yeah. So the best way, if I wanted to say, for example, this whole thing, hello there, I could quite easily, if I wanted to, do this read char with not just the input character, but also something like int I = 0, and then read the character, and every time I've read the character in, I would then store that in, say, word I, assuming that I've made this array already. So I can have an array of characters, and I can loop through running getchar, storing those elements in the array. I can definitely do that. In fact, we will definitely be doing stuff like that on Friday. Yeah. Waleed wants to know what my favorite Star Wars movie is. I think it's a tough call, but it has to be one of the ones I grew up with. And so it's probably going to be Empire Strikes Back, because it's the weirdest one in the original trilogy. So it's the one that gets a little bit dark, and it has people having to overcome great adversity, which I think is the interesting thing about the second Star Wars movie. Anyway, so Hussein, I hope that gives you enough information about it, but just wait till Friday, because I think we'll have a bit more where you'll be more equipped to deal with strings once I've explained a bit more about how they work, and us working with, words, multiple words, or taking a whole line of input raw from my user and then working with it afterwards. Waleed saying you resolved your differences. That's good. Because when other people in chat are talking about getting popcorn, then I'm like, what's going on over there? I just looked over and said, what's happening? I did look back in the break, and it looked like a misunderstanding that often happens in text chat, that sometimes it's hard to type text chat, especially if you're going quickly and you're like really in the heat of the moment, tossing around ideas, and you don't realize that what you're typing in text chat is actually quite rude to another person, and then and then it can build up. Like, I've seen enough Facebook arguments to know that sometimes people will argue when they didn't actually have a reason to be in an argument in the first place. So hopefully that's all sorted out. Yeah. Okay. Good. I'm not sure we have any other questions today, and I understand, because I think this lecture's not as super technical as some of the others can be, so hopefully everyone understood hopefully the basic process of debugging is very, very clear, and people will be able to use that now. Yeah. Okay. Thank you, Waleed. I hope that turned out okay for both of you. Actual question. Waleed is asking, will we see past exam questions? Yes, you will. I don't know if you have yet, but I think you may have already. So the weekly revision tests have a lot of past exam questions. They're not necessarily labeled as them, but they will be. So the final tutorial in the course, the week 10 tutorial, and the week 10 weekly test will be specifically labeled with exam questions. So there's at least one past... there's actually not one. I think the final tutorial has like 3 or 4 past exam questions. And the final weekly test has another 3 past exam questions. And considering the major questions in the exam, there are only probably 7 or 8 of them. I haven't actually decided. The exam is not written yet. In the exam, you kind of get a good coverage of the ideas of what's going to happen there and the depth of complexity you can expect from the exam. There's also a lot of past exam questions that are not relevant, because our past exam is actually a closed book exam where you come in to UNSW and you sit down at a computer and we don't give you the internet. We just say, all right, you're going to have to code based on what you remember. And so when there are questions like that, they're a lot harder. Sorry, they're not a lot harder. Well, they're harder to do, but the questions themselves are easier. Whereas when we're talking about having an open book exam where you can look up anything on the internet, it's actually much closer to reality for programming. Like, we program by looking stuff up a lot of the time. Like, I program with 2 monitors most of the time, and one monitor is just Google, and the other monitor is my code. So, I think that the exam is a bit more realistic now, but also a bit awkward because a lot of the answers to simple things are already on the internet, and so it's harder to test exactly what you know rather than what you can look up, which is different, you know, if I'm trying to test how well you can code. So the past questions are not necessarily valid anymore, because compared to what you'll see in your exam, a lot of the past questions from 2019 and anything earlier are going to feel too easy, because you had to memorize techniques and apply them. Whereas now, the questions are written with the assumption that during the exam, you can literally look up my lecture slides and copy paste. You know, so if I think that you could do that, then the questions have to be more interesting than that. Yeah, so hopefully that answers your question about the past questions and things. Alan is asking, you sometimes put variables inside a bracket. Can you just explain a little bit more? I'm not sure, Alan. I might need you to clarify that. If I've done it somewhere here, let me just... I'm not sure about which variables in which place you're asking about, whether they go inside brackets. Also, which type of brackets. Maybe it's these types of brackets. So some of them are very specific, as you may know. Like the while loop expression has a particular thing. Anytime I run a function and put something in it, like this, then it's definitely in brackets. But at other times, if I put something in brackets, it might be to separate it from other bits of code, like if I'm doing some maths on it or something like that. If I'm doing some maths on something, then I may want some operations to happen before others. But I'm not sure exactly which bit you are asking about. So the brackets can be used for many different purposes. Oh, wait. Are you talking about declaring variables inside of curly bracket sections? I'll wait for you to reply, see if you've... Because I'm trying to figure out exactly what... which part of me putting... Because I do lots of different things involving variables and brackets. So let me know if there's any specifics, because it might have been in the previous program that I'm talking about there. You said yes, so I'm going to assume it's the last thing that I said, which you're talking about whether I put a variable like this outside of where it's going to be used, outside the while loop, versus a variable like this that's going to be used inside the while loop. And so what I'm generally going to be doing looks like I've got a bit of lag here. I'll wait for that to come up, but I can explain it while that's recovering from whatever VLab's doing right now. Is the variable is going to have certain uses, and it needs to exist for a certain amount of time, or a certain amount of like kind of space of the code. So for this example here, the exit is something that says whether we're going to leave the while loop or not. So it has to exist before the while loop starts for the while loop to be able to check it. It has to exist outside of the curly brackets of the while loop for me to be able to make changes to it like this, and still have it... Oops. Okay. It's finally caught up with me. So, if I have this changing of the exit, I don't want it to be inside the while loop if it's going to be checked. Because if it's inside the while loop, like grid size, I can't do any testing on grid size here because it doesn't exist the first time I run it. But it also doesn't persist longer than the loop. So if I want something to exist outside the loop, like the exit, I want every time I go to the exit and come here, every time I finish the while loop and I come back to here, any changes I made to exit will stay. Whereas grid size, because it was created inside the while loop, once the while loop closes, grid size is deleted, in which case this line is actually unnecessary. Like, I didn't actually need it there at all. So, but I can't do any tests on grid size because it didn't exist outside the while loop, which is kind of good, because if I want the grid size to kind of reset and be a new variable each time, then I want it inside the loop. This can be particularly seen here where I moved column inside. So since I moved the column inside here, it means that it's recreated every time inside this loop, and it lasts until the close brackets. And when it hits the close brackets, column disappears and must be recreated next time we run it. So because this is only going to be used for this while loop here, I want the column to only be created inside this other loop, and it doesn't need to exist outside like this one does. Because row is going to get checked for this while loop, so it needs to exist outside the while loop. Column is going to get checked for this while loop, so it does need to exist outside of this while loop, but there's no reason for it to exist outside of this bigger while loop. And you could see that when I did let it persist through multiple runs of this while loop, it causes problems, because then we had to like reset it. Whereas if it's in here, it doesn't have to be reset, it will be destroyed and recreated whenever we do things. So that's the reason why sometimes certain variables will go inside the curly brackets, other variables will stay outside. Marsh was answering some question. Oh, Hussein's question about if we pass arrays into the functions, do we have them int or int star? If I'm passing an array into a function, I will most likely want to do int square brackets, so that I remind my humans who are using my code, myself, future me, and other people, that it's specifically an array. Even though you can actually have the input to an array function as a pointer, so you can do int star as an array input to a function, I like to use the square brackets because it reminds us that it's like a collection of information that's going in. And then I will use the int star if it's an individual thing that I'm aiming at that's going in, even though both of those are interchangeable. Because if you pass an array in for a pointer input, it'll understand it because it's a memory address. And if you pass a pointer in for an array input, it will also understand that. So they're functionally interchangeable, but it's like, what message am I sending to the humans that use this? If I'm saying what I'm sending you is a collection of numbers, then I'll use the square brackets. If I'm saying what I'm giving you is the address of an individual variable, I'll use int star or int or double star, whatever it is. And I do that even though either one of those will be fine syntactically. C will understand it. Sometimes I want to clarify things for humans. Hussein saying, do I have an estimation of how much time to set aside for the assignment? This is going to be different for everyone. The core part of the assignment, which is the main part of what you need to do, I would say it is, you take your medium difficulty lab exercises, so that the ones at the end but aren't challenges, I would say about 8 to 10 of those. So however long those are taking you, roughly, because they're all different, but roughly how long they're taking you, 8 of those? It's really rough. Because if one of them doesn't work, you can't just skip it and move on to something else. The assignment builds on itself. So you need to get the first stages done before the next stages work, so there's more problem solving going on. But, I was like really, really hand-wavy. The time there is 8 to 10 difficult lab exercises worth of time. That's how much time I would set aside for just bare completion of the assignment. You want to do well, you want to do extension, you want to get high marks for style, you want to be careful about what you're writing, then take more time. So that's what I'd say. Also, bear in mind, this is the notice I sent out that there's going to be a power outage on the weekend, just before the assignment is due. So plan around that. There will be some time where you won't get a compiler, you won't get submission, and you won't have VLab. So I've extended the assignment past that, so there's a little bit of extra time there. There's actually more time than you had originally for the assignment, because there's an extra day in there where CSE systems are back up. But I would plan on that weekend getting disrupted, and I would still try to finish it before the CSE power outage. Joanna's answering a lot of questions there. Yeah, I think Joanna's saying the same thing that I was. Blake is asking, Blake, have you done JavaScript? Because you say var, like someone who's done JavaScript. Is a variable declared in a loop given new memory each time? Yes, it is. So, this is way advanced, where this allocates 32 bits of memory for use, and that throws it away. And then it allocates 32 bits of memory for use and then throws it away. So if I wanted to, I could make the column outside of, and then just keep reusing that piece of memory so long as I reset it at the end of each loop, at the close of the loop. Depending on your situation, your programming language, your operating system and stuff, people can do different things like that in order to optimize memory use in different ways. But we're way beyond 1511 when we're looking at optimizing use of memory. You will learn about it eventually. Okay. Hussein's potentially going to go back and edit functions to make sure they look different. I think looking at int with the square brackets versus int with the variable name and square brackets. I don't think that you can do a function prototype without a variable name in it. But this is one of those things that's really funny because I've never tried it. Like, it's been like, oh, just do it the proper way. And then because I've been stuck in this proper way, I haven't experimented with the other ways. So I think, try it. Experiment with these other bits and pieces. This is for Hussein's question about, like, declaring arrays in in functions and stuff like that. Try it and see what your compiler thinks. Your compiler is going to be the strict line on whether something is correct C or not. Blake is saying, is at the end of the bracket that indicates the memory gets deallocated. Yeah, so the curly bracket here will always clean up the stuff that was inside it. So basically this set of curly brackets here has its own memory space. Oh, Joanna's saying it works with Clang. Well, maybe it will work with DCC then. That's interesting. I think you should try it. Try it, see if it works with DCC. So you can just not name something in the function declaration, in the function prototype at the top, but you can name it later, because you have to name it later when you're going to use it. That's interesting. Thank you for that, Joanna, because I haven't used Clang in years, and so I've gotten really, really used to just writing super, super clear code that works in DCC, but DCC might even accept it as well. So again, experiment with these things, see what you can find out. So yes, Blake, at this point in time, this variable will get deallocated. So when we're talking about allocation, we're saying that when we declare this variable, we get 32 bits of memory, and we get an address for it and everything, and it gets used. When it hits the closing brackets, this thing gets thrown away, in a sense. I mean, like, it's not really thrown away, but you know what I mean. It will no longer be accessible, so I can't do something like this. If I try to work with this, because I've said this bracket is inside, this variable is inside these brackets, it will only exist there and will not persist further. Row does, because row's at that level of indentation. If you use the indentation correctly, it can tell you these things. But column is at this level of indentation, which means once we exit that level of indentation, we go back to this level of indentation, it can't exist anymore. So you get this kind of thing where your indentation can help you interpret whether your brackets are opening or closing at different places. Okay, so Hussein's saying, so the code that actually holds the function, so not the prototype of the function, does it also need to state the parameters? Yes, it does. So do I have any demos with functions on me at the moment? One of these definitely does. The shuffler did. Oops. There was a star at the end of that, but apparently it worked. Okay. So as Joanna's saying, that we may not even need variable names, so I'm going to test that without a variable name. However, which one was I changing? Read input. Read input, this function here, in order to use the variable in here, as in the deck variable, it must exist here. I know that when we get deeper into the intricacies of the C language, there's different ways that we can do functions, and I always forget, because this is me being a C++ native speaker rather than a C native speaker. I forget, because there are some features that exist in C++ that don't exist in C. So I know that there's other ways to do functions, but I'm wary of saying anything about them because they may be C++ things. Because I know the C++ can have multiple functions with the same name, and if they've got different inputs and outputs, they will be treated as different functions. But I don't think that works in C. So let me just compile this. And see if it accepts it. It does. So if we want to, we can just not name things in the prototype here and say, you're just going to end up with this type of variable, and that's enough for you to call it. Oh, here. That's enough for you to call it because you know what variable type it needs to be. But if you want to use it within the function, you obviously... Sorry, scrolling too far. If you want to use it within the function, it has to have a name, or else you don't have a reference to it, right? You can't call it anything in here if you didn't have a name. So I think we're finding a subtlety that I've never used, because I don't like not naming things in the prototype, is that the name in the prototype doesn't make any difference. Only the types in the prototype make a difference. But then when we get down to the function itself, the name must exist for you to be able to use it. So hopefully, Hussein, that was an interesting dive. Thank you for asking those questions. That that actually taught me something that I've forgotten. So yeah, that's looks like either one of those will work. Blake's asking, does the CPU keep a register of memory addresses that are available to store values? The CPU doesn't, but the operating system does. So when we ask for something, we will go to the part of the operating system that's managing memory and will tell us what's available. The CPU doesn't keep necessarily information like that. What the CPU will do it'll be working on its own little piece of memory, which is not in the RAM chips, it's on the CPU itself. So when we say run these lines of code to the CPU. So for example, we say run the read input function to the CPU. The CPU says I will reserve some of my cache and registers. That's the names of the things. I'm glossing over some of the detail here, but it'll say some of those are what is represented by this name, you know, and it won't even be that name by the time it hits the CPU. CPU will have made this efficient, and it'll just be some kind of representation of it. But there will be 32 bits on the CPU that says this is this variable, and it will work on it. And when it's done with it, and it says, okay, I've completed my work on this variable, it'll be copied back into memory. And remember that memory layout I showed of like a C program running in memory? That's where that will end up after the CPU is finished. So it's like chunks of memory get copied from your RAM onto your CPU. CPU will do work with them, then copy them back. And it will usually go back and forth like this. So it will copy all of this onto the CPU, run all the lines one at a time, all the variables, and when it's done, it'll give the information back to RAM, and then it'll be like, all right, now we're at this point, then we go to this function, and then we'll go, okay, you wanted to shuffle, copy that onto the CPU, do stuff with it, copy it back. It's not exactly like that. It's not that simple. It's much, much more complicated. But if you're interested in that kind of stuff, there's a lot of sort of core stuff on microprocessors and operating systems and stuff like that, which will teach you all of this. I think actually 1521, which is numerically the next subject after this one, but it's not necessarily the next subject, goes into that detail on those things. Hussein, you're asking about whether we would need to give the length of an array to a function when we pass it in. We don't. The only reason I had the length here is to remind us when we're using these functions, so us as humans when we're using these functions, that I'm expecting this to be this length. I've assumed that it's that length in the function. This doesn't functionally do anything in C, because if I pass in an array, the only thing that goes into this function is the address in memory of the array that I gave it. So the thing that I create here is a copy of the array here that's passed in, and it's not a copy of the elements in the array. It's only a copy of the array variable. The array variable is the address in memory where all the elements are stored. There is actually no way, if I only give this input, there's no way for me to know how many variables are in this. So I will have no way to know where to stop. So it has to be a separate variable. So the only way that we're going to be able to pass this in is to be able to say, this is how far I want you to go in that array. It doesn't actually have to be the size of the array. I could say I only want the first 3 elements of the array, and that's fine. But if I was to write a function like this that's going to loop through an array, and I don't give it the length, I won't know when to stop. So basically array functions, any function that's going to operate on an array that needs to loop all the way through it is going to need some information about how far it needs to go. Oh, I think Joanna's already answered that. Thank you, Joanna. I think you stayed longer than you needed to. You don't have to stick around if you don't want to, but thank you anyway. All right, I'm going to wrap it up there. Answered some interesting questions, and people did a couple of deep dives into things, so hopefully you learned something useful out of that. And I will see you all on Friday. Friday we will continue what we've been doing with characters, put them in arrays, and actually write some code for them. All right, see y'all later.